hopefully not confuse you guys. All right, so we are now learning about exponentials and logarithms. So last week, we learned that there always has to be the opposite. So we learned what I call the log roll and how we can go back and forth. Remember that what we're doing are inverses of each other because they undo one another. Just like 1/4 undoes 4, and it gets us back to our identity. So when they are compared, if we have an exponent of our b to the x, and we have it next to its inverse, right? Then they're going to undo one another. That's the purpose of an inverse. That's what the inverse means. And we know that the inverse for all graphs, now that we're dealing with exponents, is the value y equals x, right? So x is our inverse value. It's that horizontal, 45-degree line, okay? So what we know about inverses now, okay, is that when they're multiplied, and this is called your composite function. You know, we've done this when we did other equations, when we talked about the composites. When they make a composite, so when we multiply them together, just like this, composite function is the only way that we can multiply the two together, then we end up with just simply x for that. So we've got our exponent here, we have our log, these are our inverses. When they're multiplied, we're going to get x. What that ends up telling us is we have two new forms that we need to memorize. And there's a lot as we go through the properties of this. Logically, we can figure them out. Some you're just going to have to memorize. It's going to be straight memorization for that. So if we were to multiply these two together, we were to make it a composite function, there are two ways that we can make the composite function, correct? We can either take our second equation and put it in our first. So when we do that, when we take our second equation and we put it in our first, we're taking this whole log bx, and we're sticking up in here as the exponent. So that's one composite function, and it turns into x. Or we can take our second equation and we can put the first one into its x space. So we have log b to the x, and we take our entire b to the x and put it in here, and it also equals x. So now we have two different forms that both equal x. It's just one is we took equation 2 and we placed it into equation 1. The second one is we took equation 1 and we placed it into equation 2. So we would write them as one is f of g of x and the other one is g of f of x. Lots of letters to tell us the same thing. Basically, we just did 4 times 1/4, or we did 1/4 times 4. That's all we're doing. We're doing one way, we're doing the other way. But what it gives us are these two special forms that can simplify an equation just by looking at it. So look at this first one. When we took equation 2, when we plugged it into equation 1 as that exponent, we now have a base on the bottom raised to a log of the exact same base. So when the base matches the base, the answer is just the equivalent value. This whole thing cancels out. Okay? When we face it the other way, and we have log, and I put it in here like log 5 of 5 to the third, when the base again matches the base, the whole thing cancels out. And your answer is simply the x value. So because these are inverses, they equal your x value. Do we see that? Okay. Ooh, I wonder where all of your little, look over that one, look at that slide, let me see if this one, okay. That's another way to write it as a thing. I'm gonna go see if I can find your boards, because we're gonna do some practice. Well, yes. Do you think you could go find me some expo markers? I cannot find my big bag. Can you round up a couple?
I have 6 here.
Oh, perfect.
I don't know
And
if
that's
that's
a 7. There. 6. So we just need 2 more. Okay. I might have. So if you want to work on those, you can. We're going to graph a little bit later, so that'll be helpful for you guys to have a quick time. Okay, so if we were to have this, 10 raised to the log 2 and log 3 to the 9x, right? In the first one, we learned last week that a log without any base written is automatically log what? Remember? If there is no number written right here, it is log 10. Great. I found 2 in my purse too, so hopefully they all work. It's not it. So if we just have log 2, this really means base 10 to the 2. So we've got 10 log 10 to the 2. What matches? Do you see anything that matches? 10. So I've got 10 raised to the 10. These match. So according to my inverse rule, it means the answer must be 2. This is my x value. Right? So we look at that and go, oh, lots of stuff, but this is a power raised to a power of the same thing, so a base raised to the base. We're going to have the same answer. Let's look at log 3 to the 9x. In this form, can we cancel anything out? No. The base and then the base for the equivalent value has to match. Can we change the base for our equivalent value? Is there a way we could rewrite 9 where it would match a 3?
3 squared.
3 squared, excellent. So I'm going to rewrite log 3, and I'm going to write 3 squared raised to the x. Now what do we have? Power to a power. Power to a power says that my 3 squared to raise to the x is now really 3 to the 2x, correct? They get multiplied. Power to powers get multiplied. So now I have log 3 of 3 to the 2x. My 3's match. My base of my log and my base of my equivalent value match. This cancels out, and my answer is simply 2x. It's the x value. Okay. Just as a verification, let's use the log rule and see if this works. If I have log 3 to the 3x and it equals something, right? We call that something x. The log rule says I write my 3 lines. What goes first? Where does my line start? 3. The next I come to is x. The last I come to, 3 to the x equals 3 to the x? Yes. True statement. Okay? So we can always go back and verify, according to our log rule, that these really do cancel out. This is just something that you need to look and memorize on it. Okay, so practice with these. You can practice on a sheet of paper. You can practice on your board. See if we can begin to identify how to simplify these logs with exponents. We had also learned 2 log rules last week, that anything with an equivalent value of 1 meant that the answer was 0, correct? Because the only way you can raise something to get 1 is to raise it to a power of 0. We also learned that when they matched, they equaled 1. So is this basically the same thing of what we're saying? For the second rule, we've just expanded. Instead of saying log base a to the a equals 1, we're now saying if there's an exponent up here, it equals the exponent. Because what really is the exponent when you don't see it? It's really 1. So all we've done is expanded our second rule of logarithms. We're going to add a couple more rules today. We already learned the first 2 last week. Okay, so for the first one, what should be the answer for 5 raised to log 5 to the 3? 3. A base raised to the base, these match, it all cancels out. Your answer is just 3. All right, second over here. Log base 3 to the 3 halves, the answer is 2. Excellent. Okay, we did this one already. We rewrote 9 as 3 to the 2x, so the answer was 2x. And this one, 10 log x,
0. 1.
should be just x. 10, because the log really has a 10 there if we don't have it written. Okay, what if I wrote e raised to the natural log of x? What would the answer, what do you think the answer would be? Who remembers what natural log means?
No idea.
Okay.
Did you read about that?
Natural log is log with a base of e. Okay, so anytime our base is e, it's rewritten as natural log. So this really means base of e. So we have a base raised to the matching base. So our answer is still just x. Right? Questions?
Is there a 1 or an L?
ln. It means natural log. And backwards.
Why did I just write N?
Yeah. Log of the natural number. But people don't speak like that. They write math like that. They just don't speak like that. Come on. Goodness. Let's be going dead. There we go. Okay. way we can look at inverses. Okay? We can basically look at our properties that we already had. We can look and say, if I have the bases matched, they're already going to be the x. Another way to look at an inverse is, when we had inverses before, to solve the equation, what did we do? We swapped x and y, and then we resolved for y, correct? So the same thing works here. We can swap x and y and just resolve for our y values, okay? If we had log 3 to the 3x and we simply asked, what is the inverse? Well, we know that the inverse of our logs is the base raised, right? So we need to know that these are inverses of each other. So if I say the inverse of 3 to the x, we would write log, my base is 3 to the x. Okay? If I start out with log base 3 to the x, my inverse is going to be 3 to the x power. We should be able to go back and forth just looking at one. This works out great if there's no h or k value, extra things added. When there are extra things added, then we need to actually swap our x and y values. Okay? So let's take this top one for example. We have ln, which means natural log. Excellent. So what is the base really that we don't see?
Log
E. So for my sake, I like to write all the things in there. Just sometimes it's easier to see all the parts. So I'm going to write that E in there so that I know that's my real base. And I have y equals natural log of x plus 1. So when we swap them, we now have x is equal to the natural log of y plus 1. And I want to get y all by itself. So the first thing is I have to separate this y from this natural log. Right? So I could say, I know that I can write the inverse of it. The inverse of a natural log or of a log is the base raised to the power. That doesn't really help me right away if I were to immediately write the inverse. And so we're going to solve for y. And this is where we get to use our log rule again. How can we rewrite the natural log of y plus 1 equals x? So when we use our log rule and we go around, we write our three values. The first one we have is base of e. The next value we come to is x. The last value that we come to is our equivalent value of y plus 1. Okay. Have I now separated my y from my natural log? My log value? Yes. Can we solve for y now? The only problem here with y is that he has a 1 attached to him. So we're going to move the 1 over, and our y is simply e to the x minus 1. And it is okay that we have our x value as a exponent there. We have just rewritten it. So initially, it would be nice if we could have just said, according to my rules, I know that the inverse is the base raised to the power. And I'm going to substitute x plus 1, and I'm going to call that maybe just our x1. And so I know that my base raised to the power. So I should have just been able to rewrite it as e to the x plus 1. Right? Base raised to the power. That's just automatically the inverse. But you can see that when we have values added, they actually get separated out. It's no longer in the power. It actually is a part of your y-intercept. Okay? And that makes sense because when we're graphing, anything that was added to the x value initially on the inverse is now added to the y value, right? Because we swapped those numbers. Okay? So how do we put all of this on paper, and how do we graph it? Okay. When we were graphing growth and decay, we were working with y equals 0, so our x-axis as our asymptote, right? So we had growth went one direction. Growth meant that the line moves away from the x-axis. We also had decay. Decay meant that the line moves towards the x-axis. Okay, so these were our two formulas. We learned that we could have a negative a value and have some on the bottom, but in most of life, you're not going to have negative amounts of money or time or things like that. So we're mostly working above our x-axis here. So according to our inverse rules, what does that automatically mean? If I were just looking at a graph and I said, find the inverse, we know we need to fold it along the y equals x-axis. And what has that done to every graph so far? When we had a parabola, oh, that one doesn't work, does it? Good thing you weren't using it. Okay, when we had a parabola and we inversed it, where did it go? Did it go upside down like that?
Flip side.
No, it went sideways. Okay, so we took, because we're folding along the diagonal, it took everything that was facing up and it laid it down sideways. So if these are exponential growth values, where do you think our logarithm values are going to lie? Sideways. Sideways, okay? So now, instead of having them growing and bounded by the x-axis, they are now going to be growing and bounded by the y-axis. So we're going to look like that instead. Okay? So one is good. This is going to be basically like your growth graph, and then we have one that looks like our decay graph. So we've taken everything that was faced up and we just laid it on its side. These are the inverse values for our logarithms. So if you are looking at a graph just to identify, if it is moving away from the y-axis, it is a logarithm graph. Okay? If you have it and it's moving away from the x-axis, then it is an exponential graph. Okay, so those are ways that we can just automatically identify what our graph looks like, and maybe if we're having to pair things up on a test. Right? So how do we actually graph them? Well, we learned when we dealt with our exponential graphs that the base of a graph always started at 0, 1, correct? That was our value that we were looking at. And that's because anything raised when x equals 0, any number raised to a 0 equals 1. So that gave us our coordinate 0, 1. So we used our exponent rules to go ahead and find a coordinate that already plugged in. We get to do the exact same thing, and we get to use our log rules to go ahead and find coordinates that we can plug in for our graph, right? So a couple of rules about our graph. These follow the same ones for exponents. With exponents, we had an asymptote. Who remembers what asymptote means?
That's the line. Eliminating line.
Yeah. A line that you can't cross. It gets closer and closer and closer, but it never actually crosses it. It's that boundary line. Can't go there. So, of course, logs have an asymptote as well. They're just the inverse. They're just the sideways of it. So they have an asymptote. Follows the same rules. If there's nothing else added for an exponential equation, the asymptote is the x-axis. Correct? And we only had it change if we had like a k value added. Okay? Same thing for logarithms. If there's nothing else added, the asymptote is the y-axis. So your asymptote is going to be, sorry, the other one was y equals 0. This one's going to be x equals 0. It's the y-axis. Okay? So it's going to be vertical. That makes sense. We've laid everything sideways. So now we're dealing with a vertical asymptote. Okay? For domain and range, range means all of our y values. If I have a graph that looks like this and it's going to infinity, okay? How many y values are going to be used?
All of them.
All of them. So the range is usually all real numbers for logarithms, okay? And what x values does it use?
All positive.
Positive, or x greater than 0. Okay, as long as your asymptote is your y-axis, then the x values for your domain are greater than 0. We're going from 0 and using up the ones that go towards infinity. Okay. We learned a couple of things when we were dealing with growth and decay. We had our basic function, y equals a, b to the x, and a was our what value? Our y-intercept. It was our starting value, so where we started, also called our y-intercept. And b was our growth or decay rate, correct? So if b was greater than 1, what was the graph doing? Growing. It was going up. If b was less than 1, it was going down. Does less than 1 mean negative numbers? No. It meant somewhere between 0 and 1. So a fraction. It was growing down. The same exact thing applies for logarithms. If b is greater than 1, it's positive. It is moving up and to the right. It is growing. Right? If b is less than 1, meaning those fractional numbers, it is decaying. And it looks like a decay function if we were to move it up and relate it to our x-axis, correct? Okay, so we have a growth function for anything greater than 1. We have what looks like a decay function for anything less than 1. Okay. We see how our numbers are relating. Any questions so far? Okay. So how do we find those special points? Because we can look at our graph, we can look at our equation, and now we can figure out what direction it's headed, what part of the coordinate plane to use, but where do we actually plug it in? We're going to go back to our very first 2 rules that we learned about logs, and we get to use those in the same way that we used our rules about exponents, that anything raised to a 0 equals 1, and anything raised to a 1 equals itself, right? We know those. We have these logarithm rules, okay? So when the bases match, we just learned that. When the bases match, it's the x value. And our x value here is an unwritten 1. So when our bases match, log a to a, so log base b to the equivalent value b, we know it equals 1. We also know that to get an equivalent value of 1, we have to raise this base to a 0. Remember, because what we're really doing is b raised to the 0 equals 1. And this is b raised to the 1 equals b. So we get to use these 2 equations and find our points. because this is y equals 1, this is y equals 0. So we already have half of our coordinate point. Do you see that if we were to write it out as a coordinate point? For the top one, we have y equals 1. For the bottom one, we have y equals 0. Now we just have to find our x values. There. Oh, goodness. Oh, too much. Right? So let's look at this one. We start with log, our base is 1/3 x minus 1. Okay, so this has a couple of different things in it that we're going to look at first. Okay. We have nothing added to our x value. So has our graph shifted left to right along the x-axis? It's the same thing all the way back from linear equations and quadratics. When we add something to the x value, it moves it left and right, correct? So we have nothing added to our x value, so it has not shifted left or right at all. So our asymptote is still our x equals 0. Okay? It's our y-axis here. Okay? So we're going to ask ourselves, how can we make this equation look like this? Right? So to get the number, we'll work from the top. To get this number 1, I want this entire equation to be the number 1. To get the number 1, I'm going to look and say my base and my equivalent value have to be identical. Right? So if we move this around, let's, x. Could I move this 1 over to the other side? Minus 1, can I move it to the other side and make it positive 1? Yes, okay. So do these look alike now?
Yeah.
These two equations look alike? Yes. So I know I can have the y value of 1 when this x matches my base. So what does x have to be?
1/3.
1/3. Okay, I have y equals 1 right here. To make it match this equation, my bases have to match. Right? Okay. Let me see what I got there. Now, to get our 0, value, okay, when x equals 0, so I want this entire part, because I know we have an x value here, but remember this whole thing is actually equal to something. We could rewrite it without an x, with a different value. That might help, so it's not so confusing. This entire section is really log 1/3a would equal an x value if I took it as a space. So when x equals 0, right, then my equivalent value always ends up being 1. When my whole thing is equal to 0, my equivalent value is equal to 1. Right? So when my value here had to be 1, this whole part ends up being 0. I know this is confusing, so we're going to work through a couple of different ones. Okay, we're having to go back and forth. So when I plug in the value 1 in my x, right here, when I plug in the value 1, this entire part that I have in green now becomes log 1/3 to the 1, which turns into what? we can replace, we're replacing our entire log base 1/3 to the 1, we're replacing that with 0. So this is a different coordinate here. So when x equals 1, I now have y equals 0 minus 1. Do you see how we replaced the entire green part with the number 0? Okay. So I have 0 minus 1 gives me -1. So y is equal to -1. So these would be 2 coordinate points that we are able to plot for this graph. We'll do a couple of more examples. This one had a k value. We went ahead and added an extra one. I'll probably do it easier. If we have, let's look at this one. Okay, if we were to get a graph, y equals log 5 to the x. Okay, let's pick a value for x. When x equals 1, what does the entire log 5 to the x turn into?
0.
Perfect. When I replace x with 1, this whole thing becomes 0. This whole section becomes 0 because I know that anything, any base with an equivalent value of 1 gets replaced with 0. Right? Now, what other number should I pick for x that would go with these rules? If I want y to equal 1, what number do I have to pick for x? 5. Perfect. So if I want y to equal 1, my base and my equivalent value have to match. So I'm going to pick the number 5. When x is 5, then y equals 1. So now I have 2 points that I can plot. So I would plot 1, 0. I would plot 5, 1. That's not 5, 1. 5, 1. It's positive, so it has to go up. So I would start at the bottom and I'm going to go up that direction. We have growth. Right. Let's do another one. When x is 0, I'm going to plug in 0. I'm going to choose 0. When x is 0, sorry, not 0. When x is 1, so you'll notice that we're plugging in the same numbers each time. When x is 1, this entire log turns into what? 0. Okay? Now, what do I want to make my x value next? What would be the next one that I would choose? 10. When x is 10, this entire log value turns into, did you say 1? Good. 1. So now I have 2 points. I would plot those 2 points. Okay? Is that making sense? Okay. Let's see what we have next. If we have something added to our x value, where now it is inside of parentheses. If you do not see a parentheses, do not consider it added to the x value. Okay? If it's written log 5x plus 2 without a parentheses, This is a k value. Okay, it is only considered an h value to be added to the x if there are parentheses there. So by assumption, these are separate. And this could be rewritten as -2 equals log 5 to the x. It can be moved away from it. When is a parentheses and it is added, we now know that our graph is shifted by what? Is it always the same number or the opposite with an h? The opposite, right? Because we've set it equal to 0. So this graph is now shifted where? -2. Right? Because if x plus 2 equals 0, then x now equals -2. So my new asymptote is no longer my y-axis. My new asymptote is now back over here at x equals -2. So now my graph starts further back. Okay, so we know that's number 1. So now let's plug in, let's walk through and plug in what 2 points could we work out. Okay, what points do we want to plug in here for log 5 x plus 2? Well, if I look over here, my first one is I want this number to end up being 1. I want my equivalent value to be 1. So how can I turn this parentheses into the number 1? Can I set it equal to 1? I want x plus 2 to equal 1 so that I can use my first rule. That means I have to subtract 2 from both sides. X has to be -1. So I'm going to say I'm going to pick the number -1. When I pick -1, I get to do -1 plus 2, erase this entire thing. I have a 1. Now log 5 to the 1 equals 0. There's my y value. Okay. What is the second x value that I want it to turn into?
3.
I want it to turn into a 5.
Oh, well, never mind.
Because when they match, I automatically know my y value is 1. So I'm going to say I want x plus 2 to equal 5. So x has to be 3. When x is 3, this whole thing turns into a 5. And then my log base 5 to a 5 turns into 1. Y equals 1. Do you see how we're being really choosy on which x values we plug in and why? So we're not automatically plugging in a 1 or a 0. We're plugging in numbers that make it turn into our first 2 forms of logs. Because we know what those answers are. So if I'm going to pick something, I'm going to pick something easy. You're welcome to pick any other number that you want and use your calculator's log function to get that. But these are a given. Got it? Okay, so what would we do on this one? And these are the questions when you are graphing. These are the 4 questions that you need to be able to answer. It will look exactly like that whenever we have a test over this chapter. Okay? 1, 2, 3, and 4. Just like that. Okay? So if we were looking at this one, log base 2, x plus 1, where is our asymptote?
-1. Wait, no, never mind. It's never.
Well, it's somewhere. Our asymptote
It's the y-axis.
is the y-axis. X equals 0. Do we ever write asymptotes as just a number? We learned that with quadratics, right? Axis of symmetry. They are a line. They need to be written as a line. So So we have x equals 0 is our asymptote because there is nothing added. Now, if I had a parentheses around here, my asymptote would be -1 at that point. So we've got asymptote. What direction does this face? Is it going to be growth or is it going to be decay?
Growth.
Because I have my base is 2. Remember, direction is based upon what your base is, because when we log roll, this 2 becomes my growth or decay factor, correct? And this is my equivalent value. So it turns into 2 to the x. Right? So our base here is the same as our base of our exponentials. It determines growth or decay. That number right there. Our direction is positive based upon the 2. Okay? So what 2 points are we going to pick? The first point we're going to pick is we want x to be 1. When this x is 1, this entire log part turns into what number? 0. Now I have y equals 0 plus 1. So y equals 1. Good job, Jace. Okay. Do we see how we replace this with 0? Yes? No? Okay. Now, what's the second number we want to pick for x? 2. We are being very intentional about what we plug in there. We're picking a 2. When I pick 2, this entire part turns into what number?
1.
The number 1. So now I have 1 plus 1 is 2. So now we have 2 points. Those would be our 2 points. 1, 1, and 2, 2. Okay. My graph is going to look like that because it's growth. What is the range? Range are the y values. What is the range for this graph?
All real numbers.
All real numbers. Excellent. What is the domain?
All positive.
Yes. And we write it for these as x greater than 0. Or you can write all positive x values. I'm okay with that too. Either way. Okay. Now, this one says natural log. We're not going to get hung up. How could we rewrite that so that we understand it a little bit better?
Log E.
Yes, log E. Rewrite it if it helps. Okay. Where's the asymptote for natural log x minus 2?
Positive.
Positive 2. So my asymptote is over here at x equals 2. Right? What direction does it face? Does anyone remember what number E is?
No idea.
2.718. It's a positive number, right? So if we have a natural log, it's going to automatically be a growth. It's going to be going out growth, unless it's to a negative exponent, because then that makes it a fraction, right? Change signs. So it's going to be growth. What 2 points are we going to pick? Let's be real intentional. What do we want x minus 2 to be? 1. Right? So when x minus 2 is 1, what x value gets us there? 3. When x equals 3, the whole thing is equal to 1, which means our y value is 0. Whoops. There we go. Okay. The other one that we want to do, and in this case, because it's an E, you can use it as a you'll just use your calculator. I won't have a natural log on the test for it. Okay? You would just pick a number and then use your computer for it, because to make this, to make it equal to 1, we would have to make x minus 2 equal to e, and that is a non-terminating number, and so you're not going to get an actual x value. So in that case, we might just pick something bigger. We know it's growth, so it's got to keep coming this way. Right, so I just picked 5 in my case, so now I had the natural log of 3. We put in 3 into our calculator and hit the ln button, and it gives us 1.6. And 1 decimal place is fine. So that's a calculator 1. Okay. So that is our wrap up for 8.4. For the rest of it, you guys should be able to finish up your homework. If you already did your homework for 8.4, great. You're already ahead of that. I'm going to try to get 8.5 and 6 then. 8.5 is pretty quick. It's properties of logarithms. We've already learned the first 2. These other ones can be memorized. There's also, logically you can work through it. Let's look at the second one. We've got a 1-to-1 rule. I wrote it up here as number 3. Log a to the x equals log a to the y. Well, if I were to rewrite log a to the x and equals, say, question mark, and use my log rule, then I have a to the question mark equals the value of x. Everyone agree with this? If I rewrite the right side, and they have to be equal to the same thing, so it's equal to the same question mark. So now I do my log roll, and I have a to the question mark is equal to y. Well, if a to the question mark is equal to x, and a to the question mark is also equal to y, then that means x is equal to y. Everyone agree with me on that one? So we get to use that and say, when we have matching bases, the logs of a matching base, the equivalent values have to be equal. They have to be equivalent. Okay? The second one is called the product rule. When we were doing exponents and we were multiplying like bases, what did we do to the exponents? Added them. When we had exponents and we were dividing, what did we do to the exponents? We subtracted them. So we learned that multiplication and addition were friends. They were a pair. And that division and subtraction were pairs, correct? They get to still be pairs because logs are the opposite of exponents, right? So everything that worked for an exponent is going to also work for a log. When we have 2 logs with matching bases, if they are added, then we can multiply the equivalent values. That also means that if we start out with multiplication, we undo it with addition. So we would separate them out with addition, as long as the bases match. So multiplication becomes addition, or addition becomes multiplication. That's called the product rule. So the same thing for quotient or division. Division has the friend of subtraction. So if they are subtracted with the same base, then now they can be divided. Their equivalent values can be divided. Or if they started out divided, now their equivalent values can be subtracted. Do you notice the order in which they're subtracted? Numerator, then denominator. Just like we did with exponents. We had to do the numerator exponent minus the denominator exponent. So they have to go in the order of numerator and then denominator when we separate them out. Right? So that's our other rules. Okay. Now, the power rule is an exponent rule. Okay. If we have a base and our equivalent value has an exponent, we can take this exponent and we can simplify it by moving it to the front. He can come down a level so that we don't have basically look like we have 3. Okay, so this would be 3 log 2 equivalent value 5. Right? So the power to power says if we have a coefficient, it can move up a level to be an exponent. If it's an exponent, he can move down and be a coefficient. So our power to power rule. These are 6 rules that you need to know how to use. When we know how to use them, we can work through a lot faster of it. Okay, ready? Was there, if you want to go back, you can look at that. There is a, did anyone print off their logarithm notes? Okay, there are errors on the answer key that I didn't do for that, so hopefully you just printed the one that was blank for it. And up here I might have even changed a couple of them. Okay, so let's look. These are some examples from your notes. On the first one, it says example 1. Your step 1 is going to be, I'm going to check these bases. So if we are simplifying log expressions, we want to try to get it as small as possible. We want to combine what we can. So for this first one, log 3 of 4 plus log 3 of 7, check if our bases are the same. Do our bases match? Yes, they're both base 3. When they match and we have addition, addition is the friend of multiplication. So I can rewrite it as log base 3. The family has to stay the same. But I can combine my 4 and 7 with multiplication. And so now it's 4 times 7. So we have simplified 2 logs into one that says log 3 of 28. If we use the log rule, we could rewrite it as 3 to the x equals 28 if we needed to actually solve it. Okay. Couple them for your notes. Okay. Number 2, we have subtraction in the middle. So when I see subtraction, I say subtraction is the friend of division. But the bases have to be the same. Are the bases the same? Yes, they are the same. Okay? So I'm going to combine my bases and get 12 divided by 3, which equals 4. So I've simplified my left side. In this one, it's actually an equal. We have an equation. So I've simplified the left side. I did 12 divided by 3. Remember, it's always the first one divided by the second one. This one's the numerator. The second one is the denominator. So I have log base 2 to the 4 equals log base 2 to the x. What do we learn from our number 3? When our logs and our bases match, then our equivalent values have to be the same. So in this case, x equals 4. So we're going to keep using all of our different properties to solve for our x. Questions on example 2? And if you didn't bring your notes, remember these slides are always available to you. You can pull them up and fill out your notes for it. Okay, so let's look at this first one. This was a practice. I think it's on there for you guys. Log 6 of 12 plus log 6 of 4. Okay, we have addition. Addition is the friend of multiplication. Can we multiply these? Are the bases the same? Yes. So for the left side, we're going to write log 6 of what? What's our new number?
So, oh wait, 12 times 48.
48. 12 times 4. Excellent. Is now equal to log 6 of x. According to rule number 3, when my bases match, then my equivalent values have to match. So what is x equal to? 48. 48 equals x. Right? Now, let's look at the one on the left. I see subtraction. Can I subtract these two?
No.
No. Okay. Is there something else that I could combine? Do I have a matcher over here?
Yeah.
Okay, so let's get the matches together.
Oh.
So we're going to leave log 3 of 8 on one side, and what are we going to do with this one?
Add it to both sides.
We're going to add it to both sides. So now I have log 5 of 4 plus log 5 of x. Can we simplify our right side? Yes, our log 5s match. I have addition, which means I do what to the numbers? Multiply. So I now have 4x is equal to log 3 of 8. You cannot simplify this any further. That would be fully simplified. So the same, like on example 3, we have 3 logs that all match. So just like with regular mathematics, we're going to do order of operations. We always go left to right. So the first operation we come to is subtraction, which means the first combination we're going to do is division. So we're going to have 24 divided by 8 first, which gives us 3. And then we do our addition, and 3 times 4 gives us 12. Same thing on this one. Now you might be tempted to just start with order of operations and go left to right. But remember, we can only do things that are the same base. And we also have to make sure that that sign stays with that value. So when I move log 2 to the 3, this negative sign has to go with him. This is a whole section. That negative is part of the log 2, 3. Right? So we're going to put like ones together. We put our log 2s together. We're going to put our like other together, log 3s together. Our log 2s are subtracted, so their values get divided. Our log 3s are added, so their values get multiplied. When we evaluated down, we got 6 divided by 3 equals 2. I now have log 2 of 2. What does rule 2 say? Anytime the base and the equivalent value equal, the whole thing turns into
1.
the number 1. So we were going to rewrite that as a 1. If we could rewrite 24 as a base of 3, then we would have simplified that one down to the x value as well. So we're always going to keep looking back. Is there another way I can simplify it? Is there another rule that I can use? Okay. So a special thing. What happens if I actually want to get a number and I want to use my calculator? Okay? Because your calculators have log, natural log, and regular log on it, but you can't pick your base. Your calculator will always work in base 10. So how do we actually change something so that we have it in base 10 and we can use our calculator? Wouldn't it be convenient to use our calculator for it? Okay. Change of base formula will change any log into base 10. This is specifically to change it into base 10. You could actually change it to a natural log too. It just changes it into the exact same base. Okay? What you will see is the way that I like to think about this, when we have our logs, remember our base is written as a subscript. So it's dropped a little bit lower below the line. So when we change our base, it's kind of already in the denominator. It's dropped a little bit lower. So we take our base and our equivalent value and we're going to divide them up to the same new base. If I'm using a calculator, I'm going to use my base 10. It doesn't matter. I could turn it into anything. We could take log 2 to the 5. I kind of say draw that line right there in the middle. Since our base is written down as a subscript, this is equal to this, and we can put any base we want in there. It could be 8 and 8, it could be E and E, it could be 125, 125, it doesn't matter. If I'm using my calculator, I'm going to make it base 10, and we don't ever write the 10 on there. It's technically 10. If you wanted to use the natural log button, then I would rewrite this as the natural log of 5 over the natural log of 2. We get to do this because our rule is what we do to one thing in math, we have to do to the other thing, right? So we get to pick as long as we do the same to both sides. So that is our change of base formula. This one is extremely valuable when you're wanting to use your calculator to find an answer. If I say, find the answer for that, well, is there any number that you can raise 3 to that will get you 7? No. Now, if I had log 3 of 9, you would know, oh, 3 squared is 9. This has the answer of 2. But I don't have a whole number integer for log 3 to the 7. So I would use my calculator and find log of 7 and divide it by log of 3. And it would give us not 2, 1 point something, whatever, some value. Okay, and 2 decimal places is usually standard. Okay, so how would you write those two? What would the first one be?
Log 7 over log 5.
Perfect. And the second one? How would we write this one? Log 25 over log 9. Okay. It's not tricky. It's a lot of information, but this one's not tricky. Okay. Okay, so that is all 8.5. 8.5, you do not have book work, you have a worksheet. Did anyone print off the worksheet and bring it? It looks like a riddle sheet. Okay, perfect. Can I borrow it, Tess? Okay. So, on this, you have 2 sections. It says expand and condense. So we have A through M is a top section and N through W is a bottom section. And then you have a riddle at the bottom. These are answers that you should have gotten. So the problems you are to work is the top section. So if we have the first one and it says log b x plus 4 squared, right? How can we simplify this? Is there a rule that we could use? Do we like to have 3 numbers stacked? No.
You move it to the front.
We can move the 2 to the front and have 2 log b x plus 4. Okay. Do we have a rule for an addition inside? No. So don't get confused. Remember, it would be multiplication makes 2 separate ones added. So this one just stays here, and there's an answer down here that looks like that. So everywhere you see this answer, it would be the letter A. Okay? If we have on here log x to the 4th over y cubed, how would we break this one up? It's currently division,
Subtraction.
so we're going to move it to subtraction. What one goes first?
X4.
X to the 4. We're going to subtract log y cubed. Questions on those? If I have, let's do this one now. 3 log x to the 4 minus 2 log y cubed. How could I simplify that and change it? We can move,
3, yeah.
right? So log x 4 to the 3rd, right? Minus log y cubed to the 2nd. When we've got power to a power, so that turns into what?
6.
4 times 3?
No, most of it.
12. This turns into 6. Now they're subtracted, so what do? We would divide. Excellent. So we would end up with log x to the 12 over y to the 6th. Okay, so that's the rules on this. You're just trying to simplify or break them apart. And then there will be an answer down below that will look like that. We have 10 minutes. Everyone need to stand up and shake.
No, it's just 10 minutes.
Okay. Okay, I know, your brains. Oh, big breath. Everyone take a good big breath if you haven't been breathing. I tend to hold my breath when it's a lot of stuff. Okay. And if we don't get all the way through it, I'll adjust homework. Okay, so do that. Okay. So how do we take all of this? Because the whole point is to actually solve something, right? How do we take everything that we know and start actually solving, finding an answer for x, finding those answers for y, okay? So we know a couple of the rules. We know that when the bases were the same, the exponents have to match. That's logical, right, if they're going to be equal. We learned with logs that if the bases were the same, the x's have to match. So we're using our properties that we have to work through and say, sometimes I can just use my properties and automatically come up with an answer. So if I have 4 raised to a 3x equals 4 raised to the 6th, and they're going to be the same thing, then obviously 3x has to equal 6, correct? So we can completely get rid of the base and just say 3x equals 6, so x equals 2 on that one. Now for the second one, I went ahead and clicked it. I have 4 raised to the 3x and 8 to the x plus 1. Initially, these don't have like bases. Can I rewrite 8 so it can be a like base? Can I find something between those that are like? Yeah. I actually am going to rewrite both sides. We're rewriting 4 as 2 squared, rewriting 8 as 2 cubed so that my bases match. I now have a power to a power, so the left side is 2 to the 6x, because I have 2 times 3x, remember? That's why it's important to know our exponent rules. I now have 2 to the 3 times x plus 1. This 3 has to do what?
Distribute.
Distribute. It cannot just be 3x plus 1. When we distribute, he's got to go to everybody, so we've got 3x plus 3. Now my bases match, and I can completely get rid of them. And we have 6x equals 3x plus 3. That's a simple linear equation. We can solve that for x. Okay? So sometimes we can just use equivalent work. Let's work this one out together. What would be the first step that you notice? Bases are not the same. Can you make the bases the same? Yes. How could we rewrite
2 and 16.
2 to the 5th, excellent, raised to the x minus 1, right? Now they match, so my equation is really 4x equals, what's the equation on the right side? 5x minus 5, phenomenal. Now we can solve for x. X equals 5. If we have our exponents just in the sky, and we have a number where we cannot make these bases the same, okay? We have to get our x on the ground. We cannot solve for an x that's in the sky. Right? We can't get an answer for him. So we have a couple of different options. We can use lots of our log rules. We can also use the log rule. The log rule works every time, right? So in this case, okay, if I want to take the log of both sides, when we take the log of both sides, it's the same as using our log rule. Remember, we could rewrite this as log base something. Okay? So what does 2 to the x turn into? Let's do it this one. Oh, and I didn't use it that way. Let me see how, let me match how I wrote it up here. What we do to the one side, we're going to do to the other side. Okay? We're going to take the log of both sides first. Okay? So remember, what we do to the one side, we do to the other side. Now, when I take the log of both sides, I get to pick what I want the base to be. We can pick any number that we want. According to our rules, what would be a wise number to pick? I'm trying to get this x alone. 2. Because if I pick base 2, what happens over here? When the base and the base match, the answer becomes the exponent. So this entire part, when log 2 to the 2, simply turns into x. Okay, so that's when we're having to think through, what do I want it to be? So now I have x equals log 2 to the 7. Can I solve this on my calculator like this? No. But I can solve it if we use change of base. Now I can plug in log 7 into my calculator, get a number, plug in log 2 into a calculator, get a number, and divide them and get an x value. Sometimes the most difficult part about this process is figuring out which step you need to use. And I understand that for it, okay? In the same way, if we went back and we used the log rule, right? We would roll around and we would take log 2 to the 7 equals x. Now we've gotten our x by itself, correct? And once again, we have to use our change of base to end up with our x value. Okay, let's look at this one and see if we can work through how to get x by itself. So we're wanting to isolate our x. He's currently up in our exponent part, right? We can log roll around to get him. I have that on this side. 10 to the log 10 of 17 equals 2x minus 3. Okay. We can also take log 10 of both sides. Now I have log 10 of 10. Those match. It erases the whole side. Okay? And we're simply left with 2x minus 3 and log 10 of 17. In that case. So if we want to solve for x, do I have that on another? Yep. We're going to isolate x. So we're simply taking, why did I no longer write 10? Because it doesn't matter. It's that unwritten one. We don't have to write it. So I'm not writing the 10, so I have log 17 plus 3 because I've moved it over. I want to get rid of the 2, so I'm going to divide both sides by 2 or multiply by 1/2. Typically, would it be okay for me to put an entire division line and put a 2 underneath here? Yes, it would be. Because there's an addition sign, it's very common to just write that in the front. But it would also be acceptable to write log 17 plus 3 divided by 2. That is also acceptable. Right? In your book, I do want to hit this. In your book, one of the examples, I don't know if anybody goes back and actually reads your examples in your book to help you get it. They talk about raising both sides as an exponent. So in this case, log 5, when we have our x value in our equivalent, they have raised both sides as an exponent with the base. Remember, why can we do that? Whatever we do to one side, we can do the other side. So if we decide to make the left side an exponent, we just have to make the right side an exponent to the same exact base. We had that rule of a base raised to a log of the same base. Once again, it eliminates it and gets rid of it. In the same way, we could have just used our log rule to log around, and this says 5 squared equals 3x plus 1. Got it? Okay, so that is all of 8.6. You will be using the 6 property rules to solve for your equations and actually solve for your x values. We have several different ways. You can take the log of both sides. You can use your change of base formula to find an x value. If you ever have matching bases, then they cancel out. Or we can raise both sides to the same power of a base. Please contact me.